Hello and welcome to our second lesson on solving rational equations. The first lesson we looked at, or in the previous topic, we saw what to do when our rational equations were proportions, when we had just one fraction equal to one fraction. Today we're going to look at what happens when our rational equation is not a proportion. Okay, so just to recap, remember a rational equation is going to contain a fraction of polynomials before and or after the equal sign. So the equal sign makes it an equation. The fraction of polynomials within the equation makes it rational. We also said that values of x that made the denominator equal 0 would have to be restricted as solutions. Okay, if the denominator was equal to 0 because a certain x value got plugged in, then we had to restrict or exclude that x value from being a possible solution. So they had to be restricted or excluded, we could say. And then if a restricted value occurs as a solution, it's called an extraneous solution. And although we call it an extraneous solution, it isn't considered a valid solution. Okay? Now I know those didn't occur in the last topic, but we will see it happen here. And then lastly, we said if a rational equation is a proportion, if we had two fractions that were proportional, one fraction equal to one fraction, then we could just cross multiply to solve. And that barely fit. Okay, we could cross multiply to solve. Now, what do we do when our rational equation is not a proportion? We're still going to start by looking for our restrictions, but we've got a different goal for solving here. There are a few different ways to do this, but my preferred method, and I've done this many ways and for many years, is to get common denominators, and let me show you why. So let's say we had a really simple equation like 1 over 7 plus x over 7 equals, let's say, 4 over 7. Now that's something that you should be able to solve without doing any work. You should be able to look at that and tell me that if I had 1 over 7, if I had 1/7, how many sevenths would I have to add to get to 4/7? Well, the 1/7 plus 3/7 would have to equal 4/7, right? If I put a 3 there, then that would be a true statement. Okay? Seems simple, right? Well, that's technically an example of a rational equation that isn't a proportion. It's more of a linear equation. We don't have any polynomials in the bottom of the fractions, but the goal is going to be the same. Now, the reason I show you this, what happens if I were to change my denominators? What if instead of sevenths I had eighths there? So if I had 1/8, how many eighths would I have to add to it to get to 4/8? Well, my answer would still be 3, right? If I changed my denominators to nines, if it was 1/9, how many ninths would I have to add to get to 4/9? Well, it would still be 3/9, right? Or if I made this 15, 1/15 plus how many 15ths would get me to 4/15? Well, it would still be 3. 1 plus 3 would equal 4, no matter what those denominators are, right? That's going to be the goal. If we can get our fractions all to have common denominators, which we've done before, then those denominators aren't affecting our problem. All we're looking at or going to be concerned with are the numerators. So the goal when our rational equation isn't a proportion is going to be to get common denominators, because once the denominators are equal, we can ignore them. We can solve just using our numerators. It's not that they cancel, so be careful with the language. They're not canceling. It's just that they don't affect our problem anymore. So we're going to get common denominators so that we can ignore the denominators and focus on solving using the numerators. Once those denominators are the same, then our numerators have to be the same too. Okay? So, cancel. We're going to start again by listing our restricted values, and then we're going to get common denominators. If the denominators are equal, then the numerators are going to have to be equal too. So if all those denominators are the same, then we can go ahead and use our equal sign to say that those numerators are going to be the same too. So then the numerators are going to be equal to. Basically what's happening is once those denominators are equal, we can ignore them. They will no longer affect our problem. So we can continue to solve using just the numerators. Okay? So get common denominators so we can ignore the denominators and solve using just our numerators. So looking at our first example here. First, we've got a couple of restrictions. What's restricted? Actually, one restriction here. If I put a 0 in, 3 times 0, it would make a 0 in the bottom of that fraction, and the same here. So x cannot be 0 for this particular equation. So we know what x can't be. And now we're going to get common denominators to figure out what x can be. So if our denominators are 3x, 1, and x, then our least common denominator is going to have to be 3x. Okay, so good news for the first fraction. I don't have to multiply anything there. The 1 is going to have to be multiplied by 3x over 3x. And then here we're going to have to multiply by 3 over 3. And then just to double check, that gives me a denominator of 3x here. 1 times 3x is 3x there, and x times 3 is 3x there. So now that all of my denominators are equal, I can solve using just my numerators. So the numerator here, which is 5, has to equal, bring down the equal sign, the 1 times the 3x, so the numerator here, 1 times 3x is going to give me 3x, bring down the minus, and then here, the 3 times the 3, the numerator here, is going to give me 9. And that's it. Okay, this is a pretty, sorry that 5 is sloppy. This is a pretty easy linear equation that's resulting here for us to solve. So we're going to get x by itself. Let's add the 9 to both sides. That leaves me 14 equal to 3x, and then I can divide both sides by 3 and call it a day. My x has to be equal to 14 thirds. Since that doesn't divide or reduce, that is my fraction answer. And that's that. Okay, it's not a restricted value. That's going to be a valid solution. And if you wanted to check it, you could plug it in using your calculator. Okay, or Desmos. Gotta love Desmos. All right, let's try that again. So here we have a restriction, one restriction. In this one, we have a restricted value of 2. If I put a 2 right there, 2 minus 2 would make a 0 in the bottom of that fraction. And since my other denominators don't have variables, no restrictions are going to occur there. So for our restricted value, x cannot equal 2. And now we need a common denominator so that we can ignore those denominators. So we're looking at a 7 and a 1 for the single terms to look at first. So that means a 7 has to be in the LCD. And then remember, binomials are considered separately. So if I have an x minus 2 there, I'm going to have an x minus 2 in my common denominator. So 7x minus 2 is it. So my first fraction has to be multiplied by the x minus 2 over x minus 2. The 4 has to be multiplied by the whole thing, the 7 and the x minus 2, and 7 and x minus 2. It's messy, but top and bottom have to be multiplied. And then here we've got the x minus 2, but we need to multiply by 7. And now again, just to double check, I have, let's see, 7 and x minus 2, 7 and x minus 2, 7 and x minus 2. All of my denominators are the same, which means now I can ignore them and focus just on my numerators. So in this numerator, I'm going to have a 2x minus 4. So 2x minus 4, bring down the equal sign. And then here, be careful, is 4 times 7 is 28, and then we're going to multiply by x, so 28 times x is going to be 28x, and 28 times negative 2 makes a negative 56. And you could have gone that route, or just so you're not too confused, if you wanted to distribute and call this 7x minus 14, and then multiply by 4, you're still going to get 28x and then minus 56. Okay, in either case, doesn't matter how you distribute, just make sure the 4 gets multiplied in there. Okay, and then lastly, we've got a negative. Be careful with that negative, it goes with that 3, and we're going to multiply it by the 7, so that's going to give us a negative 21. And there it is, no fractions left, and so we're just trying to solve this linear equation that remains. Okay, so 2x minus 4 on this side, 28x, and I'm going to go ahead and combine these like terms. It's going to be minus 77 on the side. Let me get my x's together by subtracting these two over. So now I'm at negative 4 equal to 26x minus 77. Let's get rid of that 77 by adding it over. And now I have 73 equal to 26x. And now I can divide both sides by 26. 26 and divide by 26, that's going to cancel, and 73 over 26 doesn't divide or reduce, so 73 over 26 is my solution. And it's not a restriction, so that's going to be, again, my valid solution. Now, I mentioned earlier you could check your answer by plugging it back in. Let me just show you how if you could use your calculator to do that. So on one side I have 2/7. On the other side I'm going to type in 4 plus, it should be 3 divided by, oh sorry, it's 4 minus. Let's get that typed in there, right? 3 divided by, and it should be x minus 2. So 73 over 26, and then minus 2, and it gives me that decimal. Let me just hit the fraction button here, and I could see that that does equal 2/7, which is what I had on the other side. So if you want to use your calculator to confirm, not something you need to do every time, but if you're taking a quiz, make sure you're working on the right answer there, where it counts a little more of your grade, then go ahead and verify. Okay? All right, moving right along. Same concept here. Let's start, or actually, before we list restrictions, this denominator is factorable. Factors in -6 and make -1 are going to be -3 and 2, and dividing by 1 is not going to change those. So if we look at that in factored form, we can see our common denominator has to include one of each of those binomials, an x minus 3 and an x plus 2. And we can also see our restrictions. We have two restrictions here. X cannot equal a positive 3 because 3 would 0 out two denominators, and it can't be a -2 because it would also 0 out two of our denominators. So 3 or -2, both restricted. Okay, so common denominator has one of each of the binomials, which is good news for the third fraction. We don't have to mess with that one. But the second, or the first fraction here is going to have to be multiplied by an x plus 2, and then the second one by an x minus 3, and now we're good. Both binomials, both binomials, both binomials. All denominators are equal, which means now we can solve using just our numerators, focus on those numerators. So 3x plus 6 is going to come down from that first one. 5x minus 15 plus, 5x minus 15. Bring down the equal sign, and then just a 5x from that last fraction. So that's going to be 8x and then minus 9 on this side equal to 5x. And I'm going to subtract these 8x's over. And now I have -9 equal to -3x. And then my last step is to divide both sides by -3. And that gives me a solution of x equals 3. Now x equals 3, we said, was restricted. So the only way we could, or the only solution we get here is a solution that can't actually be used because it makes a 0 in the bottom of two of our fractions. So this is one of those extraneous solutions. Okay, this is an extraneous solution. And since the only solution we have is extraneous, that means this equation has no valid solution. So there is no solution. No valid solution to this equation. Okay, if the one solution you get doesn't work, then your equation has no solution. Okay? Sorry, whoops, getting ahead of myself. Got one more here. Okay, so this is very similar to the last one. I think this would be a good place for you to try. If you are feeling pretty good about this, then go ahead and pause the video and give it a shot. Otherwise, let's see. This denominator is going to factor into an x plus 4 and an x minus 2, which is convenient because that's what we have in our other two fractions. So I know my common denominator is going to have to include both the x minus 2 and the x plus 4, and I can also see my restricted values, that x cannot equal a positive 2 or a negative 4 because positive 2 and negative 4 zero out some of those denominators. Okay? First fraction, missing the x plus 4. I need to scooch that. Missing the x plus 4. So multiply by x plus 4. Second one, missing the x minus 2. Last one has everything it needs. So again, just to confirm, x plus 2x minus 2, or x plus 4x minus 2, same thing, same thing. All of our denominators are the same, which means now we can solve with our numerators. So 2x plus 8 coming down there, plus 8x minus 16 coming down from that second numerator, and then a negative 6x on the other side. So that's going to give me 10x, and then minus 8 equal to negative 6x. Let's get these x's together. I'm going to subtract the 10 over. So that gives me a negative 8 equal to a negative 16x. And then one last step, if I divide that negative 16 over to get x by itself, then that doesn't divide, but it does reduce to a negative. Negative makes a positive. 8 over 16 is a half. And that is not a restriction, so 1/2 is going to be a valid solution. Okay? So there it is. I apologize. I didn't want to make these notes, 2 hours long here, but I meant to show, I didn't get one in here, an example where sometimes you have a quadratic equation that results after you've cleared your fractions, and if you were solving a quadratic equation, you end up with 2 solutions, and it's possible that one works and one doesn't. So if you'll just have to make sure that you're checking your work, okay? Just make sure your solutions that you're getting aren't restricted values. So again, you could have no solution. It could be that there's 2 solutions, one's extraneous, and if one isn't, then you would have a valid solution. And these aren't the solutions, but let's just pretend, just so you can see what I'm trying to say here. Let's just pretend this was our equation, and we got solutions that were like, and they're not the solutions, I'm just saying a hypothetical here. If my solutions were, let's say, 4 and 3, okay, let's say I got 2 solutions. Well, this one would be extraneous, so I couldn't count that one, but I still have one valid, so I would have the one solution that I would still count, just not the one that's extraneous, okay? So that could occur. All right, now back to our notes here. I want to show you some applications. These are just ways to apply our process of solving rational equations into some new situations. So we're going to look first at what we call work rate problems. So these are rates at which 2 people or 2 things or like 2 pieces of machinery are working to complete some kind of a task. So they typically involve 2 people or things working together to complete a task. Okay? And what happens is the amount of time that each person or each thing takes to complete a task is going to have to be converted into a rate for it to make sense in an equation format with our given information. And you're going to see that in just a second. So let's look at this first example. I'm going to come back to our bullet points there. Maybe don't write this yet if you're taking notes here because I'm going to play with this a little bit. So you have a pipe that can fill a storage tank in 2 hours. You have another pipe that can fill the exact same tank in 3 hours. How long is it going to take both pipes to fill the tank if they worked together, right? So you have some kind of a tank, okay, and you have a pipe that's filling in that tank. You have a second pipe that's filling in. It says that one of the pipes can fill it in 2 hours. Another one can fill in 3 hours. If they worked together, how quickly could they fill this tank? Okay. Now think about this. If we should sort of be able to narrow down an answer without doing any work, just using some logic here. If one of these pipes takes 2 hours to fill it alone, even though the other one's slower, if this one that takes 2 hours gets some help, then the time it takes for the both of them working together should absolutely be less than 2. Okay? So I already know I'm looking for an answer that has to be less than 2 hours, because this takes 2 hours all alone, which means now if it gets help, again, less than 2 hours. So there's that. I know my answer is going to be less than 2. Now let me just try to kind of write out in words what's happening here. So pipe, let's call the first pipe pipe 1. Okay, pipe 1 takes 2 hours, so I'm going to put that there. And then we have pipe 2, the second pipe, that takes 3 hours. And then the question is, how long does it take for them to fill the tank if they worked together, right? So together is our unknown. Let's put an X there. Now, just logically, wouldn't it make sense to say, well, if I added pipe 1 and pipe 2, that would put them together? Pipe 1 plus pipe 2 equals the two pipes together? Hopefully, yes, okay. But if I took my numbers here and I made an equation out of that, would I get an answer that makes sense? Does 2 plus 3 equals x, or 5 equals x, is that a reasonable answer? No, we already said that it's going to take less than 2 hours because the one tank is getting help, so it should not take longer if they worked together. And that is because the amount of time that it takes each pipe has to be converted into a rate. When we make the equation, the rate for pipe 1 plus the rate for pipe 2 is going to equal their combined rate. So the question here is, how do I take an amount of time and convert it into a rate? It's actually pretty easy. So we said that the first pipe took 2 hours to complete this task, right? So you start at time 0, 2 hours later, done. So how much of the job did it finish in 1 of those hours? Well, in 1 of the hours, it has done half of the job. So we could say it's done half of the job per hour. That is a rate. Okay. Or the second pipe took 3 hours to complete the task, so it started at time 0, 3 hours later, done. So how much of the job is done in 1 hour for that second pipe? Well, in 1 hour, that would be a third of the job. So that is a rate. We could say the second pipe is doing 1/3 of the job per hour. What if there's another pipe that took 4 hours to complete the job? Started at time 0, 4 hours later, done. Well, how much of the job would it have finished in 1 hour? Well, that would be 1/4 of the job. So the rate would be 1/4 of the job per hour. Okay, maybe you see where I'm going with this. So hypothetically here, let's say there's another pipe that takes X amount of hours to do the job. How much of the job will be done in 1 hour? So what are we doing to go from the amount of time that it takes to the rate, from the amount to the rate, or from the amount to the rate? Well, this would be 1/x of the job per hour. All we're doing is taking the reciprocal of the amount of time it takes. 2 over 1 flipped over is 1 over 2. 3 over 1 flipped over is 1 over 3. 4 over 1 flipped over is 1 over 4. X over 1 flipped over, 1 over x. And if it happens to be a whole number, you can think about it as just sticking a 1 over it. So 2 hours is half the job per hour, 3 hours is a third of the job per hour, and so on. Okay? So here, pipe 1 is doing half of the job per hour. Pipe 2 is doing a third of the job per hour, and together they're going to do 1/x of the job per hour. So the rate for pipe 1 plus the rate for pipe 2 is going to equal their combined rate, and solving this equation is going to get us a logical answer. So the amount of time, that's this bullet again, the amount of time it takes for each person or machine or whatever to complete a task has to be converted into a rate, and to do that, we want to do that because the sum of the individual rates will equal the rate for the people or things working together. So we can make that logical equation out of their rates, and the reciprocal, again, reciprocal of the amount is the rate. The reciprocal of the amount of time it takes is the related rate. So put a 1 over a whole number, right? If it took 4 hours, then the rate would be 1/4 of the job per hour. If it took 2/3 hours, then it would be 3/2 of the job per hour. So you just want to put a 1 over it if it's a whole number, because that's technically the reciprocal. Or again, just flip the fraction if it's already a fraction. Okay, so here is our equation. Now we just need to get a common denominator so we can solve. Okay, this is not a proportion, so we're not going to cross multiply. So for 2 and 3 and x, our least common denominator is going to be a 6 and an x. So I'm going to multiply by 3x here. I'm going to multiply by 2x here. I'm going to multiply by 6 here, and then 6x, 6x, 6x. My denominators are all the same, which means now I can solve using just my numerators. So I have 1 times 3x, which is 3x, bring down the plus, 1 times 2x is 2x, bring down the equal, 1 times 6 is 6. So that's 5x equals 6, and if I divide both sides by 5, my answer is x equal to let me more space here. X equal to 6/5. Now, x equal to 6/5. Now, if this problem had no context and we were solving, and I would say leave your answer as a reduced fraction, improper, whatever, it's fine. But remember, with a word problem, we want to make sure our answer makes sense to the problem. So if I said, how long is it going to take these pipes to fill the tank if they were working together, you're going to say, oh, it's going to take them 6/5 hours. Probably not, because we don't speak in fraction. So I think converting this to a decimal would be more reasonable. And as a decimal, this would be 1.2. So if you said, it's going to take 1.2 hours, I think that would be reasonable. And we knew it was going to be less than 2, so that definitely makes sense. Now, even 1.2 hours is a little sketchy. What would that be in hours and minutes? So 0.2 of an hour would be 0.2 of the 60 minutes. So that would be 12 minutes. So the best answer would be 1 hour and 12 minutes. But if I put something like this in your practice, unless it was multiple choice, you could select that. If it's inputting the number of hours, you would have to go with the decimal, just because I'm a little bit limited in Canvas and how I can ask the questions for those numeric problems. It specifically wants that decimal. Okay, so you should be able to convert to hours and minutes, but whatever. 1.2 hours, totally fine. Okay, so here's another example. Let's see. Together, Kara and Brooke can complete their Saturday chores in 15 minutes. Working alone, Brooke takes an hour to complete the chores. How long does it take Kara working alone? So we have this time Kara, plus we have Brooke. And if we add them, we're going to get them together. And it says that together, Kara and Brooke can complete their chores in 15 minutes. So let's put a 15 over here for together. It says working alone, Brooke takes an hour. Now be careful, I don't want to put an hour here if I've put minutes here, because now I have two different units. So I'm going to make that 1 hour 60 minutes. So 60 minutes here for Brooke. And then it says, how long does it take Kara working alone? I don't know. I'm going to put an X there for Kara. Now this equation wouldn't make any sense because I would get a negative answer if I solved, but remember, we want to convert these amounts to rates. So Kara is going to do 1/x of the chores per minute. Brooke is going to do 1/60th of the chores per minute. Together, 1/15th of the chores per minute. And now I can get a common denominator and go about my solving. So common denominator here, we could use 60x, multiply here by 60, multiply here by x, multiply here by 4x, and again 60x, 60x, 60x. All of my denominators match, so now I can solve using my numerators. So 60 there plus x there equal to 4x there. Let's get the x's together. That gives me 60 equal to 3x, and then dividing by 3, I can see x has to equal 20. And x was Kara, so we're going to say Kara takes 20 minutes to do her chores. Not bad, Kara. Your sister Brooke, a little slow. Okay, last one here is one for you to try. Just to save time, you're not going to go through all the solving. We just want to try the setup. I think that's the harder part of this. So if you want to pause and give it a try, just try to set it up, okay? Don't worry about the solving. So it says it takes Sarah 3 times longer to complete a task than it takes Lucy. Together, they can complete the task in 5 hours. How long does it take each of them working alone? So we've got Sarah in this one, plus we have Lucy in this one, and if we added them, that would put them together. Okay, so it says it takes Sarah 3 times longer to complete the task than it takes Lucy. Now, does it tell us anything about how long it takes Lucy? Sure doesn't, which means Lucy is going to be our variable, so we're going to put an x there for her. Now, if Sarah takes 3 times longer, then we can put a 3x there for Sarah. And it says together they can complete the task in 5 hours, so I'm going to put a 5 there for together. So 1 over 3x, and then 1 over x, and then 1 over 5 converts those amounts to rates, and those two individual rates combined will equal their rate together. And there's your equation. Common denominator of 15x would clear out the fractions so that you could solve, but not necessary. Okay? All right, so hopefully those aren't too bad. Were great problems. I actually kind of like those. These ones, however, not so fun for people. Distance, rate, time problems tend to pose a bit of a challenge, so I'm going to try to help you organize the data. The good news is you do get to use a formula here. So with a distance, rate, time problem, you're going to have two people or like two trips, but for each of the people or each of the trips, you're looking at a distance that they've traveled, a rate at which they've traveled, and a time for them to travel. Okay, so it's distances, rates, and times for two things, either two trips or two people, whatever it is. Okay, so we're going to try to organize all that information into a table, and then we're going to try to use a formula to solve. And there's a formula that connects distance, rate, and time, and it's one that should make sense. So, for example, if I said that I was traveling on the freeway at 60 miles per hour for 2 hours, if I went 60 miles per hour for 2 hours, how far would I have gone? Well, 60 miles per hour for 2 hours, right, would be 120 miles. So this distance was equal to the rate here multiplied by the time here. So distance equals rate times time. And if I wanted it to be t equals instead of d equals, to solve for t I would have to divide the r over, so distance divided by rate. Or if I wanted it to be r equals, I would divide the t over, so distance divided by t. So three formulas, all technically the same formula, three versions of the one formula. So one of the following formulas, distance equals rate times time, or we could say that time equals distance divided by rate, or we could say that rate equals distance divided by time. Okay, and hopefully in organizing the table, you're going to be able to determine which of those versions of the formula is going to be helpful. Okay, and I'll show you. So for example, we have Olivia that bikes 15 miles per hour faster than John does on his mountain bike. And in the time it takes Olivia to bike 80 miles, John bikes 50 miles. We're going to find the rate for each bicyclist. So let's see. Let's organize this into a table where we put in our distance and rate and time for two people. We have Olivia and we have John. Okay, so it says that Olivia's biking 15 miles per hour faster than John. In the time that it takes Olivia to bike 80 miles, John bikes 50. So distance for Olivia is 80. Distance for John is 50. So she's going 50 miles, she's going 80 miles, he's going 50. Now for the rates, it says Olivia bikes 15 miles per hour faster than John does, but we don't know anything about how fast John is going. So John's rate is going to be our variable. Let's call it x. If she goes 15 miles per hour faster, then for her, we can put x plus 15. Okay? Now, time is where we are going to decide which formula that we want to use. Okay? Since I don't want to introduce another variable. It says in the time it takes Olivia to bike the 80, John bikes 50, but I don't know how much time that is, and I don't want to put another variable into that column. So since the t column is left, I know I want to use the t equals formula, and here I see that t is equal to distance divided by rate. So if I take my distance and divide it by rate, it's got to equal my time. So in that time column, I can actually take the distance and the rate I have, in this case the 80 and the x plus 15, and divide those. And the same thing for John, I can take the distance of 50 and divide it by the rate of x. And now since she can do this in the same time he can do this, that means that these two times for Olivia and John have to be equal. So our equation is going to be 80 over x plus 15 equals 50 over x. John's time has to equal Olivia's time. Her time for 80 miles is the same as his time for 50. Okay, now good news for solving here, this is a proportion. So we can go ahead and cross multiply. So we're going to distribute 50 to the x plus 15, and then we're going to multiply 80 times x. So we're looking at 50x plus, 750 equals 80. And let's subtract those 50x's over. And that's going to give us 750 equal to 30x. And then let's divide the 30. And we're done. X is going to equal 25. So X was John. So then we know that John was going 25 miles per hour. John's going 25 miles per hour on his bike. That's pretty fast on a bike. And then Olivia is going at a ridiculous speed, 15 miles per hour faster. 25 plus 15 means she's going 40 miles per hour on a bike. She's freaking flying. I don't even know if that's possible. Yeah, but we're going to go with it since this is a hypothetical, okay? So there it is. Let's try another. I've got if 40 mile per hour traveling Olivia wasn't enough excitement for you, you've got a canoeist in this next problem. So a canoeist can paddle 2 miles upstream on a certain river in the same time that she can paddle 6 miles downstream. So notice in the last problem it was 2 people. Here it's 1 person, but there are 2 trips. 1 trip upstream, 1 trip back down. It says the speed of the current is 2 miles per hour, and we're trying to find the speed of the canoeist. So again, let's try to organize this into a table. Distance, rate, and time is going to go into the table. And it's 1 person, but she's making a trip upstream, and then she's making another trip back downstream. And I can't fit all that in there nicely, so let's just say up and down. How about that? Okay, so it says she can paddle 2 miles upstream, distance up is 2. In the same time, she can paddle 6 miles back down, so distance down is 6. The speed of the current is 2 miles per hour. We're going to be looking for her speed. So her speed, we don't know what that's going to be. The speed of the canoeist, we're going to call that x here. But we do have to factor in the speed of the current. So there's going to be 2 things going on in our rate column, our speed column. Hopefully you understand current. If you're going upstream, that means you're fighting the current is going against you. So if the current's going 2 miles per hour and you're going against it, you're basically going to lose that 2 miles per hour from your speed. And if you're going downstream, you're going with the current, then you can go ahead and add the speed of the current to your speed. So the current, speed of the current, 2 miles per hour, we add and subtract from whatever the rate is, in this case, the person here. Oops, where'd it go? Okay, sorry. Add and subtract from x, whatever the speed is, okay? In this case, it's x. So we don't know her speed, but upstream, I know she's going to be going 2 miles per hour slower. So I would subtract the 2 because she's going 2 miles per hour slower. She's being slowed down by the current. Downstream, she's going with the current. So again, I don't know what her speed is, but she's going to be 2 miles faster because of the current. Okay, so now we're just like in the last problem. Time, we don't know how much time it takes her to go up or how much time it takes her to go back. All I know is it's the same time for both trips. So I don't want to introduce another variable there. Again, because that t column is blank, it's telling me to use the t equals formula, and t is equal to distance divided by rate. So I'm going to take the distance of 2 divided by the rate of x minus 2, take the distance of 6 divided by the rate of x plus 2, and again, those 2 trips took the same amount of time. She went upstream 2 miles in the same time that she went downstream 6 miles. So our equation is going to be 2 over x minus 2 equals 6 over x plus 2. And again, we have a proportion, so we can just cross multiply to solve. So 6 is going to distribute to x minus 2, and 2 is going to distribute to x plus 2. So we're looking at 6x minus 12 equal to 2x plus 4. Let's get some of these terms together here. Let me subtract these 2x's over so that 4x minus 12 is equal to 4. Let's add over the 12 so that 4x is equal to 16. And almost there. If 4x is equal to 16, all I have left to do is divide by 4. And that tells me x is 4. Again, out of context, we could just box that in, but what does that x represent? That is the speed of our canoeist. She's going 4 miles per hour upstream, 2 miles per hour because the current's slowing her down, downstream, 6 miles per hour because it's speeding her up. So the canoeist is traveling at 4 miles per hour. That's, I don't know, fast or slow. Seems slow, but on a canoe in the water, maybe it's fast. I don't know. All right, I got one more here for you to try again. I just want you to try the setup. Don't worry about the solving piece. That right now is not the hard part. Okay, so let's see. A tugboat in the Hudson River is traveling at 10 miles per hour. It travels 24 miles upstream and 24 miles back downstream in a total of 5 hours. What is the speed of the current? So we're going to have a distance, a rate, and a time. It's one tugboat making a trip upstream and then making a trip back down. Okay? So it says it's going 24 miles up and 24 miles back down. So the distance up and the distance back, 24 miles both ways. And we actually know that the tugboat is going 10 miles per hour. This time we're trying to find the speed of the current. So for the rate, I know the tugboat's going 10 miles per hour, and then the speed of the current, let's call that x. We're going to have to subtract that when the tugboat's going upstream because it's going to be slowed down by that current. And then the 10 miles per hour is going to be added to the speed of the current when the tugboat's going down the river, downstream, because it's going with the current because it's going faster. Okay, so again, our time column, be careful. It says that the trip up and the trip back makes a total of 5 hours. So we know something about the time, but we don't know how much of the 5 hours is for the trip up. We don't know how much of the 5 hours is for the trip back. Obviously, the speeds are going to be different because of the current, so I can't just guess at how much each trip took. So again, this is going to tell me to use my t equals formula. So take the distance, divide by the rate, take the distance, divide by the rate. Now this time, those two trips aren't happening in equal amounts of time. It says these two trips take a total of 5 hours. So what we want to do is add the time up, which was 24 over 10 minus x, to the time back down, which is 24 over 10 plus x. Those two trips together took 5 hours, and that would be the equation that we could solve to figure out the speed of the current, which is, I know, just like super useful information. I don't know. This is just a chance for us to apply the process of solving and a little bit of logic and organization. Okay? So there that is. I don't think I boxed this last one in, so my OCD is kicking in. And there you have it. All right, plenty of stuff for you to try to work on for the next practice. So give it a try. This will be the end of the unit. So as you're working along and getting ready for that quiz, feel free to reach out if you need some extra help. All right, guys, take care.